All right. Can you see my screen?
Yes.
Good. Yeah. First of all, what so wonderful to see Ehsan kind of, from being a grad student to winning a whole bunch of awards and grants and setting up a nice group. So first of all, it's just an awesome day to just be with you, Ehsan, here. And hello, everyone. And I've been to Rochester a few times. Wonderful place. And I guess you guys back in story with Kodak. So you're on the front page of Wall Street Journal, so that's good. um, you know, any publicity is good, right? So today I'm going to talk about two projects. One is on contact tracing and one on privacy preserving machine learning, both related to COVID. And as San said, feel free to interrupt me. It's a very short presentation. Feel free to interrupt me and we can go on. And then also want you to go and download the app and play with the Slack. I heard from my son, you guys are thinking about your class projects. So, it's a very open platform in that sense. So kind of the main story here is that anytime you have a distributed data that you need for machine learning, let's say, then the data is unavailable because of privacy or trade secrets or regulation. And so what we can do is we can use privacy preserving algorithms to support machine learning algorithms that have been decentralized. And think about smartphone as a mental model. So if data is locked away on smartphones and you still want to train a machine learning model from the data, how can you train it without sucking up, without asking the users to give the data on their smartphones, right? This is the two projects. One is the contact tracing, which has spun off into a foundation now, and the privacy preserving split learning. So this is the challenge we have, right? On one hand, we have on this privacy utility axis, for Google Maps, we willingly give away our location to Google so that Google can do calculations of traffic and show us in real time, the red spots and the green spots, right? Great utility, no privacy. For health data, we don't give away our health data, so it stays in silos, and so we get very little utility. So would there be an equivalent of Google Maps for our health data? If you can have a bird's eye view into everything that's going on, you can probably solve some of the most important problems in health overnight, right? And so the goal for privacy preserving machine learning is to have privacy and utility at the same time. And when I use the word privacy, it's not just privacy for an individual, like the way you would think about on Facebook or Twitter, but it's also privacy between organizations, which is they don't want to share data amongst themselves because of HIPAA regulations or because of trade secrets and so on, right? So privacy is kind of a catch-all term that prevents individuals or entities to sharing data with each other. So let's take a concrete example. Like if we had about 2 million hospitalizations for COVID-19, if we had everybody's chest X-rays, we can very quickly figure out if this person needs different kind of care. But the best data set that's out there for chest X-rays right now only has 14,000 images, right? And so we cannot train these networks, with such small data sets. It's a missed opportunity, and all of this has to happen in real time. I mean, imagine if from the patients in China and Korea back in January we could get all these results, right? And now things are stabilizing because more people are writing papers, but still machine learning hasn't played as big a role. So on the horizontal axis, I want to think about kind of different ways we can achieve privacy. Some of you may be familiar with k-anonymity, which is maybe the simplest form of anonymity, and you can do a lot with that. Then there's differential privacy, where you would obfuscate your data. And then probably the best form of privacy is homomorphic encryption. But if you start using these techniques, then on the vertical axis, which is what you can do for machine learning or analytics, you have kind of very little returns. So if you start encrypting it, all you can do is statistics. If you do differential privacy, you can still do some inference. But to do full-fledged machine learning, either you anonymize, but then if you use an overlapping data set, it can all be decoupled. It can be deciphered, or you use something called smashing. And two techniques have emerged in the last few years. One is called Federated Learning from Google, and the second is called split learning, which is from our group at MIT. And the basic idea behind both these techniques is to share wisdom, but not raw data. So if you think about the smartphones, I would just want the wisdom from the smartphones. I don't need to ask raw data, especially personally identifiable data. So I'm going to come back to this. So coming to exposure notification and contact tracing, the classic method is you want to use smartphones, Bluetooth-based, neighborhood calculations, notify if you're cross-path with somebody who was later diagnosed positive. Once you get that notification, ask the person to do some kind of self-assessment and diagnosis, and finally create some public health and coordination tools for public health, right? The challenge is, how do you guys do it on campus at Rochester? Do you have your own test facility? How do you guys do it right now?
We have a chat bot that you talk to before you come into campus, and that's pretty much it.
Okay. And are there testing facilities on campus yet?
Yes.
Okay.
The university owns a major hospital chain, and it's a major research hospital. We're about 20th in the nation in NIH funding, and we have fairly substantial testing capacity. They're currently testing approximately 400 randomly chosen students a week.
Wow. Okay. That's pretty good. And what's the total population for students?
About 6,000 undergrads, about 5,000 grads.
Okay, so 400 is not enough, but so 400 daily, you said?
Weekly.
Okay, so it's not enough, but it's a good start, right? The bigger problem is that pure exposure notification. How many here are familiar with exposure notification? Just raise your hands. I can see your screens. Kind of the Apple, Google exposure notification. Have you heard about it?
Oh,
okay.
Yes.
Yeah, maybe half of you have heard about it. So I'll explain a little bit more. So the idea is two phones exchange Bluetooth tokens constantly, and if one of those people is turns positive at some point, then everybody who came in contact with them over the last 14 days automatically gets an exposure notification. And the way it works is the two phones exchange Bluetooth tokens, and once the person is infected, diagnosed positive, then they upload all their Bluetooth keys to the server. And every healthy person downloads those keys every day and sees whether the downloaded keys are the same as the keys that you heard over the Bluetooth channel. If they're the same, then that means you are too close to the person who was declared infected later on. Okay, it's as simple as that. And there are a few second order details. I won't go into it. There's a notion of rotating keys and things like that, but I won't get into that. But that's the basic idea. The challenge is that even if you build something like this, that just tells you you're close to somebody. But so what? I mean, you might be wearing masks, you might be keeping social distance, you're at the same place at the same time with this person in the grocery store. Maybe it doesn't matter, or maybe it matters because you're at a wedding and you're not very careful. So there are many other things that play a role beyond just exposure notification, okay? And so diagnosis, testing, quarantine, exiting the quarantine, all these things need to be managed through these apps. The difficulty, if there was a software company could just come in and deploy this, no big deal. The challenge is how do you do this in a privacy preserving way, right? Which means that no phone number, no name or email address or student ID number or things like that should be asked for, and still be able to manage everything out there. Of course, campuses are not doing this at all. They're asking your name and your ID number, everything before you do the test. So there's no privacy at all on campuses. But at some time there'll be rebellion, and all the campuses and workplaces and towns will start hearing it. But right now, let's, from a computer science point of view, our goal is to provide this in a privacy preserving way. So this is a pretty complicated problem. So we spun out a nonprofit out of MIT in April, and we're helping many states and nations launch their apps, these complicated apps. And right now we're already in 5 US states and territories and multiple nations as well, right? About 50 million people. And it has very quickly become, as Hassan said, we started back in March. So it has become world's largest open source nonprofit for digital pandemic response. So I just, in the chat, I posted the link to the Slack channel. About 2,000 people are writing research papers, doing projects, collaborating with each other, from, places all over the world, from people who are high school students who are writing amazing papers, to college students, grad students, scientists from many companies and universities, to government leaders. They're all on that Slack channel, just exploring every possible idea for COVID-19. It's just mind-blowing to watch that. And also, we're also very fortunate to get long-term philanthropic funding. And then in terms of research, you have to solve many, many problems. This co-presence problem that I talked about, like how do you figure out that two people are at the same time at the same place? Can be done through Bluetooth, can be done through GPS, through Wi-Fi, through cell phone tower data. But you can also imagine other exotic ways to do it, maybe through ultrasound, maybe by looking at motion sensor. If you're in the bus, two people in the bus at the same time, your motion sensor will be somewhat similar as the bus is bumping around, right? So you can figure out the two people are at the same time at the same place, and so on. And of course, how do you do this in a privacy-preserving way? Because you're not going to upload the MAC addresses of every Wi-Fi router you saw on the server. So this privacy-preserving co-presence detection, becomes a challenging problem. Any questions or thoughts so far?
Yeah, I kind of had one to get your opinion on. Why do you think it's the case that we're so willing to give up our location data to, get all these utility out of it, but when it gets to public health information about yourself, people show a lot more reluctancy?
Yeah, that's because Google and Facebook have hired 1,000 PhDs to solve one problem and one problem alone, which is how do you make that platform addictive enough so you spend one extra minute? So just think about it. 1,000 PhDs every day are working on one problem, which is how will you spend one extra minute on the platform? And by doing that, they have convinced you that you can trust them, right? The same way you are achieving privacy by just blowing out, your face with bright sunlight.
Yeah, I'm dying over here. I gotta be honest.
No personally identifiable data there. We see you, Curtis, now. So on the other hand, public health just doesn't have that manpower to make you addicted to their services. It's more like a nanny state. That's why medicine is so boring for most people. It's like, I'm going to tell you what's good for you, what you should eat, how much you should sleep, how much you should walk. Come on, like it's just that's why medicine, information from doctors, and my wife is a doctor. It's just, on the other hand, with Facebook, they never tell you spend one extra minute, but somehow you end up spending one extra minute every day, right? So that's the problem. So I'm with you. I mean, for some reason, even some, app from a foreign country where we don't know what's happening to your data, we're willing to share it, but to our own government, we don't, when all the regulations are in place already. But nevertheless, I mean, I'm not an Apple fanboy, but on Google, when you go from point A to point B, Google knows everything. It knows point A, it knows point B, it knows the route you took. On Apple, if you use Apple Maps, Apple does not know what A is, what B is, and what route you took. So it's able to provide that information to you in a privacy-preserving way, right? And Apple has just made a decision to be completely privacy-preserving, which means that even Apple does not know, even a rogue employee within Apple doesn't know, and even the server doesn't know what A was, what B was, and how you took the route. And Google has said, send all the data to Mountain View and just trust us, we'll do the right thing with it. And what we need to do is get to this model where, the data doesn't even get sent to a server in its raw form, right? And if we achieve that, then we have a win-win. It goes back to my first slide on privacy versus utility. So that should be our goal. If if public health authorities can get to that point, then we're like, sure, yeah, let's do it.
Thank you.
Other thoughts?
I would argue that there is some utility in health data. I mean, increasingly people are, they have their watches attached to them. And I know I do analytics on my heart rate and things like that. So, I mean, I think maybe positioned the right way or positioned in a different way or marketed in a different way, people might be willing to make some trade-offs of health data privacy for some utility if they're interested enough and think there is enough utility in it.
Yeah, but Erin, the point is that instead of trying to convince people and by that almost mislead people and take the risk of data breach and identity fraud and rogue employees and the next Snowden, or Cambridge Analytica, why not just get into a world where the data doesn't leave your devices in an identifiable form, but you can still provide them all the services, just the way Apple can.
Yes, no, I get the objective, and that's why I don't have a Facebook account, and I use DuckDuckGo and all of those other things. So I get the objective. I'm just sort of saying there to certain people there is utility in health analytics and health data.
Yeah. So let's do an experiment. I want you to open your phone and open the just a iMessage or whatever you use, text messenger, SMS messenger, and then type I as a first letter. And as you know, in the bottom, it'll give you 3 choices for next word, right? So just take the middle one. So for me, it's I. It gives me 3 choices: am, can, or have. I'm going to type can, right? And just take the middle one, right? Take the middle one and keep clicking. Click, 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 click. It'll keep adding an extra word to it, right? All right. It'll just keep writing something seemingly interesting. Okay. Just click about 100 times. Okay. And I want some of you to just read back to me. Who wants to go? Go for it, Michael.
Mine's really boring. I'm going back and I'm going back and I'm going back and I'm going back and.
All right. Who else?
Mine's a little creepy. I think they have the same number for you, and I think we should get them to get the stuff to go back, and then they get them, and they are still going to get the stuff.
Wow.
All right, who else?
I've probably revealed way too much.
Who else?
Okay, I'll go. I can't believe how I feel like this was the first thing to say. I love that. I can get it. Haha. I love that.
So this is your life. Okay, and now I'll do the next one, which I don't want you to read out, but just for yourself. Type love, L-O-V-E, and then space. Okay, and it should either reveal the person you write to quite a bit, right? Either their first name or whatever you call them, or things like that, right? Now here's the question. Apple and Google are not looking at your text messages. They're end-to-end encrypted. Okay. So how are they able to predict what's going on your phones? Because it's a next word prediction scheme, right? There's a machine learning model that's being trained from billions of phones, literally, and they're able to predict the next word. So in case of Michael, that's his life. Let me go back. In case of Erin, she's always trying to help people, trying to debug the problems for them, right? For Curtis, he's always cracking jokes and laughing, right? So these are kind of your personalities, right? And the phones have trained in a privacy preserving way, because end-to-end encrypted. Remember, Google and Apple cannot see your text message, the content of your message, but the machines are still being trained. Anybody knows? This is a pretty well-known technique, actually.
Is it the federated learning?
Yes, it's a combination of differential privacy and federated learning, right? And so what's happening is the machine learning model for next one prediction is being trained partially on billions of phones, and those models are being combined, right, on average, right? And there's some additional stuff that happens. So for example, if you're writing your credit card number, then it doesn't want to remember that. So it adds differential privacy, it adds some blur to it, and so on. So it won't overfit, basically, right? And then when the model comes down to your phone, it has to do some kind of a transfer learning. So it trains one more time, so that when I type love, the next word is my wife's name, and for you it's something else, right? So it also trains those models so they don't get confused, right? It doesn't start writing somebody else's name when I say love, right? So it's kind of an interesting world we live in, where we are able to provide all the services in a completely privacy preserving way. So if Google and Apple can already do that, why can't they do the same thing for everything else? Why can't they do this for, predicting if somebody's going to get a heart attack, or, if they start going to, a lot of places that could be suicidal? All those models are already there. There's enough data on people's phones to solve some of the most important societal problems. But because of the data silos, we cannot train those models, right? And that's kind of my passion of how do we extract data and create a bird's eye view so that we can start solving these problems, even though at first blush, it seems like nobody will share the data with you. So that brings me to the second part of the problem. And I gave you the example of the chest x-rays. So basically this problem I told you is basically a small data problem, not a big data problem anymore, because the data is all siloed on phones, and I want to create something meaningful out of it. And as Ehsan said, federated learning is one way to do it, which is every client can take the data and train it partially, and then send it to the train it partially the neural networks, and send, in simple words, send the model weights to the central server so it can take an average. In reality, you send the gradients and you look at different epochs. There are a lot of second or third order details, but the basic idea is, you partially train an average, right? And this works reasonably well. A different method that's coming from group called split learning is the idea is that you convert each data point into its feature vector, okay? And you send only the feature vector to the central authority. And from the feature vector, it can do inference or it can do training. Pretty simple idea. The challenge is that the feature vector is not privacy preserving. It turns out from the feature vector, you can reconstruct the original data, with pretty good accuracy. So we have to create a new type of a feature vector, which we call smashed vector or smashed wisdom, so that from the original data, we can convert it to a smashed representation. And the smashed representation is still good enough for inference or training, but is irreversible, okay? So the way you do that is you take a neural network, you split it. The early part of the network executes at the at the client, and the later part of the neural DNN executes at the server. And the early part, we call it the smasher, and the smasher converts your data point into this smashed representation. And rest of the process is similar to a traditional TNN process for supervised learning, right? And then if you want to do any kind of distributed machine learning, then you have all these challenges with compute, data, bandwidth, machine learning specific issues and so on. I'll send you the slides, so I won't go into the details. And so the challenge is, how do you manage all of these things? And it turns out that using this methodology of converting data into a smashed representation becomes 100 to 1,000 times better than traditional federated learning. So it's very suited for smartphones. And we have shown this on many benchmarks already, especially for medical data. And then maybe the most important problem to solve here is, as I said, do I have a better slide? Yeah. The most important problem is if you have input data X and you smash it and create intermediate representation Z, then from Z, it turns out you can go back to X very easily. In fact, you can train a GAN, a generative adversarial network, that will take you back from Z to X very easily in most networks. So we have to create a different type of a smash representation where the distance correlation between X and Z is actually very low. At the same time, the cross entropy between the labels is extremely high for training, right? So the second part of the term is the same as before, but the first part of the term reduces the distance correlation, and that's how Z becomes somewhat private with respect to A. You cannot go to X from Z. So that's kind of the basic idea. Here is an example of tissue images or histopathology images. If you use a traditional CNN, and the top row are different tissue images, and if you just send them through a traditional neural network, and from the representation, you can actually reconstruct the original images, no problem at all. And using the technique I just mentioned, if you go all the way to the bottom row, then it turns out the bottom two rows, then it turns out that we can use them for infrastructure training on the server, but the server will not be able to reconstruct the original images from Z because the server gets Z, right? That's the basic idea. And we have another technique called splintering, which is different than split learning, where we can take a data vector and we can create linear combinations of it, ask for service, get a label, and bring the labels back and reconstruct the original label as a linear combination of those labels, right? I won't go into the detail about that. So that's kind of the two main projects I wanted to cover. One is contact tracing for COVID-19, and the other is how do you create this privacy-preserving machine learning that can be used in COVID and anywhere you have challenges with data silos.